A deep, almost surreal stillness defines Crater Lake. Its surface often appears like polished glass, reflecting the sky with such clarity that depth becomes almost impossible to judge. Visitors standing along its rim frequently focus on its volcanic origin, the violent past that formed this caldera in Oregon thousands of years ago. Yet beneath that calm, beneath the steep walls and the vast column of water that plunges nearly 1,943 feet, or about 592 meters, lies a far less visible hazard, one that does not glow, erupt, or announce itself with fire. It moves silently, shaped by gravity, water pressure, and the fractured skeleton of an ancient volcano. What happens when a lake this deep sits inside a steep-walled volcanic basin that is still structurally evolving? What happens when sections of those walls weaken, fracture, and begin to shift under their own immense weight? And what happens when all that mass, rock, sediment, and water moves at once? The danger is not hypothetical. It is embedded in the structure of the caldera itself. Crater Lake occupies the collapsed summit of Mount Mazama, a stratovolcano that once towered over the surrounding region before a catastrophic eruption approximately 7,700 years ago emptied its magma chamber and caused the summit to cave inward. The resulting caldera formed a steep-sided basin that gradually filled with rainwater and snowmelt. Today, the lake is one of the deepest on Earth, holding roughly 4.9 trillion gallons, or about 18.7 cubic kilometers, of water. The walls that contain this immense volume are not uniform solid barriers. They are composed of layered volcanic deposits, lava flows, ash, pumice and breccia, interspersed with zones of weakness. Over time, weathering, freeze-thaw cycles and subtle tectonic adjustments have continued to alter these walls. While the lake appears stable, the geology beneath and around it tells a more complex story of slow movement and structural stress. Fault systems exist in the broader region, including those associated with the Cascade Range, where volcanic and tectonic processes overlap. Crater Lake itself is not isolated from these forces. Beneath and near the caldera, small-scale faults and fractures accommodate stress changes within the crust. These structures may not produce frequent large earthquakes, but they contribute to the long-term weakening of the caldera walls. The slopes descending into the lake are among the steepest found in any large body of water. In many areas, they plunge at angles exceeding 40 degrees, composed of loose and semi-consolidated volcanic material. This creates a condition where stability is constantly dependent on friction, cohesion, and the balance between gravitational pull and structural resistance. When that balance shifts even slightly, the results can be sudden. Subaqueous landslides, also known as underwater mass movements, are a key concern. These events occur when sections of the lake's inner walls collapse and slide into the water. Evidence of past collapses has been identified through bathymetric mapping of the lake floor, which reveals irregular deposits and debris fields consistent with previous slope failures. These are not minor occurrences. Some deposits suggest that significant volumes of material have moved in single events. The mechanism is straightforward but powerful. A portion of the caldera wall becomes unstable due to a combination of factors: fracturing, water infiltration, seismic shaking, or gradual erosion. Once the resisting forces are overcome, the material detaches and accelerates downslope. As it enters the lake, it displaces a large volume of water. That displacement generates waves that propagate across the confined basin. In a lake as deep and steep-sided as Crater Lake, these waves can behave differently from those in open water. The confined geometry amplifies their height and energy. Instead of dissipating gradually, the waves reflect off the caldera walls, interacting and potentially increasing in amplitude. The result is a localized tsunami, an inland wave event capable of surging upward along the lake's rim. The concept of an inland tsunami may seem counterintuitive, yet it is well documented in similar environments worldwide. The key factor is rapid displacement of water. In coastal settings, this is often caused by undersea earthquakes. In enclosed basins like Crater Lake, Landslides are the primary driver. The scale of such an event depends on the volume and speed of the collapsing material. Even a relatively modest slide, involving several million cubic yards or a few million cubic meters of rock and sediment, could generate waves tens of feet high, potentially reaching heights of 30 to 50 feet, or roughly 9 to 15 meters, along certain sections of the shoreline. Larger collapses could produce even more significant waves, particularly if they occur in deeper parts of the basin where water displacement is maximized. Timing is another critical factor. Unlike oceanic tsunamis that may take hours to reach distant coastlines, a wave generated within Crater Lake would reach the rim within minutes. There would be little to no warning for anyone near the water's edge. Trails, observation points, and boat landings situated along the inner slopes could be directly exposed. The risk is compounded by the variability of the caldera walls. Not all sections are equally stable. Some areas show more extensive fracturing, while others consist of looser deposits that are more susceptible to failure. Geological surveys have identified zones where past collapses are more likely to have occurred, suggesting that these areas remain points of potential weakness. Seismic activity, even at relatively low magnitudes, can act as a trigger. The region surrounding Crater Lake experiences occasional earthquakes, typically minor but sufficient to induce shaking. In a setting where slopes are already near the threshold of stability, such shaking can initiate movement. The presence of water further reduces stability by increasing pore pressure within the material, effectively decreasing friction and making it easier for material to slide. Seasonal factors also play a role. Snow accumulation during winter months adds weight to the caldera rim and slopes. As temperatures rise, melting snow introduces additional water into fractures and weak zones. This combination of added weight and increased moisture can weaken structural integrity, particularly during spring and early summer. Freeze-thaw cycles contribute by gradually widening cracks, creating pathways for water infiltration and further destabilization. The depth of the lake itself intensifies the consequences. At nearly 1,943 feet, or 592 meters, the vertical distance allows collapsing material to accelerate significantly before reaching the lake floor. This increased velocity translates into greater energy transfer to the water, enhancing wave generation. In shallower lakes, similar volume movements might produce smaller waves due to reduced acceleration and displacement. Another factor often overlooked is the composition of the submerged slopes. Over time, fine sediments settle along the lake floor, forming layers that can act as weak planes. When overlying material collapses, it can trigger secondary failures within these sediment layers, effectively increasing the total volume of displaced material. This cascading effect can amplify the initial disturbance, producing larger and more complex wave patterns. The geometry of the caldera further influences wave behavior. Crater Lake is not a perfect circle, and its internal contours vary. Certain areas may focus wave energy through a process known as constructive interference, where reflected waves combine to form higher peaks. This means that wave height would not be uniform around the lake. Some areas could experience significantly larger surges than others, depending on their position relative to the slide. Historical records of the lake do not document large tsunami events in recent times, but the geological evidence suggests that such events have occurred in the distant past. The absence of recent occurrences does not indicate safety, rather, it reflects the long intervals between major slope failures. Geological hazards of this type often operate on timescales that exceed human observation. The broader tectonic context adds another layer of complexity. The Cascadia subduction zone lies offshore, where the Juan de Fuca plate is being forced beneath the North American plate. While Crater Lake is inland, large earthquakes originating from this subduction zone can transmit seismic energy across vast distances. A major event along this boundary could produce shaking strong enough to affect the stability of slopes within the caldera. Closer to the lake, smaller fault systems within the Cascade volcanic arc accommodate regional stress. These faults may not generate catastrophic earthquakes individually, but their cumulative activity contributes to the ongoing deformation of the crust. Over time, this deformation influences the condition of rocks forming the caldera walls. Hydrothermal processes, though less visible than in active volcanic systems, may also play a role. Hot water circulating through fractures can alter the mineral composition of rocks, weakening them chemically. This alteration reduces cohesion and increases susceptibility to failure. While Crater Lake does not exhibit the same level of hydrothermal activity as some other volcanic regions, subsurface processes cannot be entirely ruled out. Taken together, these factors create a scenario where the most significant hazard is not an explosive eruption or lava flow, but a sudden water-driven event triggered by the collapse of the lake's own boundaries. The water that gives Crater Lake its beauty also amplifies its danger. The same depth that inspires awe provides the energy needed to generate powerful waves when disturbed. Monitoring efforts have improved understanding of the lake's dynamics, but predicting the exact timing of a slope failure remains extremely challenging. Instruments can detect subtle movements, changes in seismic activity, and variations in water levels, yet the transition from stability to collapse can occur rapidly once critical thresholds are crossed. The rim of Crater Lake, rising hundreds to thousands of feet above the water, offers numerous vantage points. Roads and trails trace its edge, bringing visitors close to the steep internal slopes. While these locations provide unparalleled views, they also lie within potential reach of wave run-up should a significant displacement event occur. The height that a wave can climb depends on its initial energy and the slope it encounters, with steeper inclines allowing water to surge higher before losing momentum. Boat operations on the lake introduce another dimension of exposure. Vessels operating near the water's surface would have limited time to respond to a rapidly approaching wave. Unlike ocean vessels that may ride over long wavelength tsunamis, smaller boats in a confined basin could be severely impacted by steep, high-energy waves. The possibility of a large-scale internal wave event within Crater Lake becomes more consequential when examined through the lens of speed, confinement, and reaction time. The physics governing water displacement in such a deep, enclosed basin reveal how quickly a localized disturbance can transform into a basin-wide hazard. When a mass of rock detaches and accelerates down the caldera wall, the transfer of momentum into the water is nearly instantaneous. Energy is imparted not gradually but in a concentrated burst, forcing the water upward and outward at the same time. In open ocean environments, waves generated by disturbances often spread across vast distances, losing height while maintaining energy over long wavelengths. Inside Crater Lake, that dispersion is restricted. The basin acts as a natural amplifier. Wave energy reflects off the steep walls and then intersects with incoming motion, creating complex interference patterns. Instead of diminishing quickly, the water can oscillate violently, with multiple wave fronts crossing paths in rapid succession. This oscillation introduces a secondary hazard beyond the initial surge. Even after the first major wave reaches the shoreline, returning water mass can draw material back into the lake, only to be followed by additional surges. This back-and-forth motion, sometimes described as siege-like behavior, can persist for extended periods, depending on the scale of the initial disturbance. In a deep basin measuring nearly 1,943 feet, or about 592 meters, from surface to floor, the time it takes for water to settle can be significant. The configuration of the lake floor plays a critical role in shaping these dynamics. Mapping has revealed terraces, sediment deposits, and old slide remnants scattered across the depth. These features can redirect motion, focusing water towards certain sections of the rim. A collapse occurring on one side of the lake does not guarantee that the highest wave will strike directly opposite. Instead, energy can be refracted and concentrated in unexpected directions, increasing danger for areas that might not appear directly exposed. The steep inner slopes surrounding the lake also influence how far water can travel vertically once it reaches the shoreline. Wave run-up is not solely determined by initial height. It is shaped by slope angle, surface roughness, and momentum. On near vertical sections of the caldera wall, water can surge upward dramatically, potentially climbing dozens of feet, reaching elevations of 40 to 80 feet, or roughly 12 to 24 meters under strong conditions. These elevations place portions of trails, viewing platforms, and other accessible areas within potential reach. Rockfall triggered by wave impact adds another layer of complexity. When water surges upward with significant force, it can enter cracks and dislodge already unstable sections of rock along the rim. This means that an initial landslide could initiate secondary collapses above the waterline. These secondary events may not generate new major waves, but they can contribute debris that further destabilizes the environment and complicates evacuation or movement along the rim. The relationship between water level and hazard intensity is another critical consideration. Crater Lake does not experience significant fluctuations compared to reservoirs or river systems, yet even modest variations in water level can influence how a wave interacts with the shoreline. Higher water level reduces the vertical distance a wave must climb to reach human-accessible areas, effectively increasing exposure. Lower levels may slightly reduce direct inundation risk, but can expose additional loose material along the slopes, potentially increasing the likelihood of slope failure. Weather conditions can subtly alter the outcome of a displacement event. Strong winds can precondition the surface, creating existing wave patterns that interact with incoming tsunami waves. While this interaction is complex, it can either amplify or reduce local wave heights, depending on alignment and timing. Visibility, meanwhile, affects reaction time. Fog, precipitation, or low light conditions could obscure early visual cues, leaving little opportunity for individuals near the shoreline to respond. Seasonal visitor patterns also intersect with hazard timing. Warmer months bring increased activity along the rim and on the lake itself. This coincides with periods when thawing and water infiltration into rock may be at elevated levels, subtly increasing instability in certain zones. The overlap between peak human presence and periods of potential slope weakening introduces a compounded risk dynamic that is not immediately visible but is structurally embedded. Transportation routes encircling the caldera follow the rim at varying elevations. While most of these roads sit well above typical wave run-up projections, certain segments dip closer to the inner edge. In a high-energy event, spray, debris, or localized overtopping could affect these areas. More importantly, any disruption caused by rockfall or ground movement could temporarily isolate sections of the rim, complicating movement away from affected zones. Communication challenges emerge in scenarios where events unfold within minutes. Unlike coastal regions equipped with extensive tsunami warning networks, a local event at Crater Lake would rely primarily on immediate situational awareness. There is no large buffer of time between cause and impact. This places emphasis on recognizing natural warning signs such as sudden water retreat, unusual sounds resembling rock movement, or visible collapse along the slopes. The geological framework surrounding Crater Lake continues to evolve. The remnants of Mount Mazama's collapse did not settle into a permanent equilibrium. Instead, they established a system that slowly adjusts under ongoing tectonic and gravitational forces. The influence of the Cascade Range remains present, not through constant dramatic activity, but through persistent low-level deformation and stress redistribution. To the west, the distant but powerful Cascadia subduction zone represents a large-scale source of seismic energy. A major rupture along this boundary, capable of generating earthquakes of magnitude 8 to 9, would transmit shaking across the region. Even if reduced by distance, such shaking could act as a trigger in a system already balancing on thresholds of stability. The connection between offshore tectonics and inland slope behavior is indirect but significant. Closer to the lake, Minor faulting and crustal adjustments contribute to localized stress. These faults may not individually produce large events, yet their cumulative influence over time shapes the mechanical properties of the rocks forming the caldera walls. Microfractures expand, bonds weaken, and the internal structure becomes more susceptible to sudden failure when conditions align. Water infiltration remains one of the most persistent and understated factors. As precipitation and snowmelt seep into fractures, they exert pressure from within. This poor pressure reduces effective stress, making it easier for rock masses to slide. In some conditions, water can also act as a lubricant along existing planes of weakness, further lowering resistance. Over extended periods, this process transforms structurally coherent rock into fragmented material poised for movement. Sediment accumulation at the base of slopes adds to the system's sensitivity. Each small rockfall contributes to a growing layer of loose material on the lake floor. While individually insignificant, these deposits can collectively reach a point where they themselves become unstable. A primary landslide entering the water may disturb this accumulated sediment, triggering a larger composite movement that exceeds the volume of the initial collapse. If you found this breakdown insightful and want more deep dives into hidden geological risks like this, make sure to like, share, and subscribe. Tap that hype icon to help this reach a wider audience so more people understand what is really happening beneath places that seem completely calm.